conversation today too. You're probably not alone. Okay, so let's just very quickly review what we talked about towards the end of Friday, and that was we talked about friction. The kinetic friction force corresponds to one surface sliding against another, and that grinding kind of pushes back against the direction of motion that the object is sliding. And it's got a fairly simple law that's not exact. It's a crude approximation. We'll investigate this a little bit experimentally, to what degree it's true tomorrow in lab. But the kinetic friction force, how strong it pushes back against the direction it's sliding, depends on the materials, and that's contained in this coefficient of kinetic friction, mu sub k, k for kinetic. And here, Giancoli would probably call the normal force F with a subscript n, but the normal force, the harder it's pushing down against the surface, the bigger the friction force you get. And then we also talked about the static friction force. Let me flip forward so that everything's on here. And static friction force is a little bit more confusing. There are two cases that we might think of. Well, there's only one kind of static friction force. Static friction force means two surfaces are against each other, and they're not moving relative to each other. They're not moving, we're talking about static friction. In almost all cases, the static friction force, as long as the thing is staying stuck on there, the static friction force just balances out whatever other force components are parallel to the surface. So if you add up all the forces that are trying to shove it one way or the other along the surface, the static friction force will balance those out and make it zero because it's not budging. If it were budging, we wouldn't be talking about static friction. So as long as it's not moving, that's pretty simple. You just make the sum of the forces zero, and one of the unknown forces in that case would be your static friction. The one that looks superficially like the kinetic friction but really isn't used the same way tells us about the breaking point, because we all know that if I push hard enough, at some point it's going to start moving along the surface. This one here doesn't tell us about any old static friction force, but the maximum magnitude force that static friction can push back on. If you push it, if you try to apply any more force, it can't push back anymore, and it breaks free, and then we're not talking about static friction force. And this formula tells us how to calculate the breaking point. Mu static, again, that mu, the coefficient of static friction, depends on the materials at the sliding interface. And it also depends on the normal force, F sub n, or I just wrote it as n here. Okay? So let's see how to apply those. There's a problem that I think I went through in the videos, but let's go through it again because things get a little bit slightly more complicated than we had with the inclined plane with no friction. So again, here's, let's see, we're given both types of coefficients of friction, kinetic and static, between a box and an inclined plane that it's perhaps going to slide on. What's the minimum magnitude force applied to the box in the direction parallel to and up the plane to get it moving? So the idea is, if I've got the box here and I'm pushing along the direction of the plane, if I don't push hard enough, it just sits there. Push a little harder, still just sits there. What's the minimum I can push with to cause it to break free? That minimum is going to correspond to that maximum static friction force, right? I want to push with the amount that corresponds to friction pushing back with the maximum static friction force. That means I'm going to draw a free body diagram where I'm imagining everything's stuck there, but it's right at the breaking point. And if I even pushed a hair harder, it would start going up the plane. So let's draw that free body diagram, but imagine we're drawing this and it's in the situation where I'm pushing with this minimum value. Of course, if I push any harder than that, it still will start moving, but we're looking for the minimum that it could be. And if this is the minimum, then static friction is going to be pushing back along the plane with its maximum value that it can. And so that's the one that corresponds to mu static, which here is 0.2, times the normal force. I know it looks like 0.2 newtons. That maybe I should have written it 0.2 times Fn, the normal force. Of course, we need a normal force in there, otherwise the whole thing would just go falling through the plane, right? The normal force from the plane keeps it from falling through the plane. And then by virtue of the fact that we're close to Earth, we have a weight force. So those are the four forces in the free body diagram. And we're imagining all of this is taking place at the breaking point. And as we've done before, even though there's no acceleration in this case, later on, I'm going to ask a follow-up question that will involve some acceleration, and it will accelerate along the plane. So I'm going to choose, as usual, my axes parallel to and perpendicular to the plane. Because I know if it's going to start accelerating up the plane, there would only be one non-zero component for the acceleration, whereas if I drew them horizontal and vertical, that wouldn't be true. Okay. You might not, the first time you do this problem, think to do this first, but after a while, you'll sort of wisen up to the fact that, look, if I do sum of the force x components equals max, that means along the direction parallel to the plane, one of those forces depends on the normal force, which is along the y direction, and I'm not going to know that normal force unless I first do sum of the force y components equals may. So if you wrote down sum of the force x components equals max, you'd quickly realize, well, besides the force I'm looking for, that F min, there's another unknown, that normal force that I'm calling n here. So, and the only way to get at it is by doing sum of the force y components equals may. Okay? These two forces that are along the plane, one forward up the plane, one down the plane, have zero y component in my coordinate system, right? The n is all y components, so it comes in with a plus sign, just all of n. And then I need the y component, which is this side of the right triangle down here, of the weight force, right? Find its y component, and it's going to be negative. So I put a minus sign in there. I know the length of the hypotenuse is 20 times 9.8. And, you know, you can either do SOHCAHTOA kind of stuff or say, to get from the hypotenuse to the side I want that corresponds to the y component, I pivot through the angle, and for some reason I like that, and cosine at the same time, so I multiply the hypotenuse times the cosine. So this right here, the left-hand side of this equation is the sum of the force y components, and that's equal to may. Why is that 0 here? Yeah, I mean, well, so it's not moving at all in this diagram. We're imagining it's a situation where it's about to break free, but everything's just sitting there, so there is no acceleration. But even if it were accelerating, even if it were moving, it would be moving along the plane, and that means its y coordinate would be constant, right? Its y coordinate isn't changing, even if it were sliding up the plane, so certainly this one should be 0. AY is 0. And that allows me to solve for the normal force, or Fn, if we were using the G. I see the advantage of that. It's sort of confusing writing it next to newtons, but this is the normal force, so many newtons. Once I've got that, then I just do sum of the force x components equals max. And again, we're imagining it's not moving, so ax is also 0. And there are 3 non-zero x components we're talking about here. F min comes in with a plus sign in my coordinate system because I chose plus x up the plane. The mu static times the normal force, that magnitude force comes in with a minus sign because it's pointing down the plane. So I have mu static times the normal force that we just found out. And then I need the x component of the weight force, which corresponds to this side of this little right triangle. And hopefully, you know, after you do some of these problems, you'll start to get used to this right triangle always appearing there. And so you'll immediately know, oh, okay, that angle, yeah, it's going to be the same as the angle of the inclined plane once you get used to it. To go from the hypotenuse to this side down here, I have to go across the angle, so I multiply by the sine of 20 degrees, and it comes in with a minus sign. All right, so once we do that, we can solve for F min. It's not such an interesting number, 104 newtons. So if you're pushing with 104 newtons up the plane, if you push any harder, it would start to slip and probably accelerate. And in fact, here's the add-on question I've put here, which with the also up there, the last sentence. If that force is maintained, if we keep pushing with 104 newtons, and it's hard to not do that, right? If you're just slowly increasing your force and it starts to slip, you tend to, at least until your body decompresses, keep pushing with that same force. So all of a sudden, it's not going to start moving with constant velocity. It's actually going to start accelerating. We'll see why. So if we maintain that force of 104 newtons, once it started slipping, then we're not talking about, this would be the wrong force to put in there. It's not the maximum static friction force that would be applied down the plane. Now it's the kinetic friction force because it's grinding against the surface once I've broken it free. And we want to know what's the acceleration of the box then, and then what's the box's speed after it's moved 1 meter. Again, I just threw a little kinematics problem on the end. So I'm going to use essentially the same free body diagram, but except this is mislabeled here. This should be now the kinetic friction force, whose formula is mu kinetic, that's 0.1, times the normal force. That's the only thing that would change in the free body diagram. And now we know this is constant at 104 newtons, so we would just make it 104 newtons. So now if I sum force x components and set it equal to max, I have plus 104, right? That's our force that we're still applying even after it's broken free. Then I have the kinetic friction force, mu kinetic is 0.1 in this problem, times the normal force, and you'd find out if you did F net y equals may. Since we only changed something along the x direction, the y force summing equal to ma doesn't change at all. We've only changed something along the x direction, so it doesn't change the fact that the normal force is the 184.18. And we've still got the x component of this force there. Now they're not equal to 0 anymore because it's moving. We're assuming it's going to accelerate, and so that's equal to the mass of the thing in the free body diagram, 20 kilograms times the unknown acceleration. Solve for the acceleration, something a little bit less than 1 meter per second squared. And then we answer that last question, what's the box's speed after it's moved 1 meter? Well, I'm given a displacement. I want to know a speed. The relationship between displacement and speed is that squared velocity equation, right? We want to know the final speed. We know its initial speed, it's starting from rest, and we now know its acceleration is positive in this case, and we can solve for delta x after we square root the whole thing, 1.36 meters per second. So you can see no one step of this is too difficult, but you put it all together and there's quite a few things strung together. So you got to get used to, it's not nearly so complicated if you don't have an inclined plane. So the inclined plane problems are kind of the most difficult when it comes to friction. Okay, I think that's the end of this. So let's now look at problems 9 and 10, and I want you to try them yourselves. Where is my version? Let's see, here we go. So in 9, let's just sort of see what's different about it. We've certainly got an inclined plane and a box on it. We're given both coefficients of friction. Sounds familiar so far. In this case, the idea is you've got this plane there. Someone put a box on it, and you just look at it, and the box isn't slipping. And the question is, what is the friction force magnitude from the plane? How much is the plane pushing on the box along the direction of the plane? What's the magnitude of that friction force? And the idea is nobody's told us it's about to slip. So we have no business using that mu static times the normal force. Rather, we should just assume that it's some smaller force than that. And then part B, you should at least try to start to set up. If it's not about to slip, what if I keep increasing the angle? If I slowly increase that angle, at some point it will start to slip. Probably everybody has that intuition. See if you can find out how to figure out at what angle it slips. flip back here just in case anyone wants to refer to that. Mm-hmm. Do you mean what this problem is asking for? The magnitude of the friction force. So it looks like you've turned your box on top of the plane into a free body diagram, right? Now, I can't really tell here, but it looks like your weight force, this one down here, is pointing in the wrong direction. It should be pointing straight down, perpendicular to the bottom of the plane. And then, yeah, so you've got the right angle labeled in there, but your weight force better be going towards the center of the Earth. Right, so, and then, so in this case, no one is pushing in the direction up the plane, right? I mean, you can think about it, if friction weren't there, if it were a frictionless plane, the box would slide down, right? So I know to hold it in place, the friction force has got to be pushing in the direction up the plane, but there's nothing additional pushing down the plane in this case. So I think there would be three forces in your free body diagram. A normal force. I just thought I saw it. Yeah. Oh, okay, yeah. Yeah, that looks good. And so that force going up the plane is the friction force. And so you can just give it a symbol. The length of that arrow is Fs for static friction force. And sum of the force x components equals 0 because it's just sitting there.
So it would just be the force that counteracts the horizontal force.
Yes. So it's a 2 kilogram block. I'm just checking your details now. 20-degree incline plane, yep. So in this case, you don't really need the normal force, even though you've calculated it. You've forgotten a little g right there, right? It should be mg times sine of 20. Just like you had up there, right? You did 2 times 9.8 times the cosine of 20. You need a 2 times 9.8 times the sine of 20. Well, it's neither vertical nor horizontal. It's the x yeah, that one's the x component, and your x component is parallel to the plane. Now that's not straight up and down, and it's also not horizontal. It's your x-axis is tilted at an angle. But the idea is that weight force has magnitude mg always. So we just say the length of that weight force vector is mg, and then we project out the x or y components from the triangle. Mm-hmm. Yeah, when you say Vx, you mean the x component of the weight vector. Is that right? Yeah. Well, in this case, that's true.
So if that's the only one pointing in the other direction, and we want to find
That's right, because there were only 3 forces, and the normal force is perpendicular to the direction that we're summing over. In this case, you're doing sum of the force x components equals max, right? And this one's x component is 0, so there are only 2 that could contribute. We just take their x components, one's positive, one's negative, and one we actually have to do some trigonometry to figure out the correct side of the right triangle. But yes, you're doing it the right way because there are only 2 forces. Now, it's possible that, a problem could say, well, oh, in addition to that, there's someone pushing up the plane with an additional 20 newtons or something, and then there would be 3 forces. Not only would there be friction, but there'd be some other force from a finger that's pushing up there or something. But in this problem, there weren't. That's a good question. And in certain kinds of problems, it can be pretty confusing. But in this case, we know the friction has to be pushing in the direction. It always pushes along the plane or whatever direction the thing would be sliding on if it started to slide. And the only question is which way on it. And in this case, you can imagine if there were no friction, it would immediately start going down the plane. So what's going to keep it from going down? That additional friction force, which is holding it up the plane. Right? It wants to start sliding down the plane, but friction's pushing in the other direction to keep it from going down the plane. Friction in that one was pointing that way is because imagine in this case, I change the situation where the box is there on the plane and I say, now I'm going to add another force where I'm going to push up the plane on the box so it's just about to break free. Well, if the friction force weren't pushing back, I would be accelerating it up the plane, right? But because the friction force is pushing back against me. But it can be confusing. If I've got an object sitting here, friction can point both directions, right? Now, if I'm pushing in this direction, which is from your left, friction is pointing to your right. Now it's pointing to your left because it's opposing a force that's going. Maybe I had that backwards. It's hard for me to turn it around in my head, but yes, it's pointing. I can switch the direction. It's the same way. By adding extra forces, I can make it so the object maybe in the absence of friction might go up because someone's pushing on it up. Or if that person's not there, in the absence of frictions, it would go down. So friction, you can infer which direction from that. Okay, should we go through A together? I think it's probably worth just the ritual of setting it up because again, what you want to be comfortable with when Wednesday's exam comes is this process of, for certain key types of problems especially, things in elevators, sitting on scales, we've seen a lot of those, certainly inclined plane kinds of things. Drawing the relevant free body diagram, putting the axes on it, they're going to pay off, and then doing F net equals MA components. So the first thing I would do is just draw a sketch because this didn't come with a sketch. The angle here is 20 degrees. It's a 2-kilogram box. And the idea is it's just sitting there. So what forces are acting on it? Well, certainly weight. The length of that vector I just drew is mg. And we already know we're going to want to maybe get these components, and this angle, hopefully you're getting the idea, is the same as the angle of the inclined plane. You could do a little proof to yourself, but you don't have to once you're gotten used to that. And then if it weren't for a normal force perpendicular to the plane, I'll call that Fn here, then it would be falling through the plane. And if those are the only two forces acting, it would start sliding down the plane. So there's got to be a friction force, in this case, pushing it up the plane. I'm going to label it as Fs because the idea is you plunk this thing on the plane, we just observed it's not moving. So we're talking about a static friction force, but it's probably not the maximum. I just chose a random angle and it just didn't move, so it's probably not about to break free. And in this case, I want to know how big this has to be. This, in this case, doesn't involve the normal force, so I don't really need to solve for the normal force in part A. Maybe I'll need to in part B, but let's try to get away with not doing it for right now. So in part A, well, I need some axes as usual. Doesn't really matter whether I take plus x to be up the plane or down the plane, but I'm going to take mine to be up the plane. Sum of the force x components equals max. The Fs is all along the x direction, and it certainly is a positive vector. That's what we want to solve for, so that's our variable. And then this force has a non-zero x component that comes in with a minus sign, and besides the minus sign, we're looking for this length on the right triangle. So the hypotenuse is 2 times 9.8. We want 2 times 9.8 times the cosine of 20 degrees. And those I add to 0 because it's just sitting there. Nothing's accelerating, so ax is certainly 0. And so, yes, it's the sine. Thank you. Right, we're looking for across the angle there. We're looking for this side. Thank you. And then I can solve for Fs. 6.704 newtons is how big it is. So the important thing here is it's not about to break free. When these kinds of problems appear on exams, you know, a lot of people are tempted to use that mu static times the normal force, which is not appropriate here, and you don't need it. So you'd just be doing more work because you'd have to get the normal force first, and it would be incorrect anyways. It doesn't. It would be incorrect because that mu static times the normal force is the formula for the maximum static friction force that could be exerted when it's just about to break free and start sliding. That's mu static times the normal force. In this case, just because I have a tilted plane, slightly tilted, and I put a box on it, it doesn't slide, it doesn't mean that it's just about to break free, and if you just gave it a little, you know, blow of air, it would start sliding. No, it's probably pretty firmly rooted there, and you know, it could take quite a bit more force before it starts sliding. There's no indication that it's about to slide. Is that enough on that, Sam? Yeah. Okay, and then, so that's A. Thankfully, we didn't have to get the normal force. But in B, it looks like we're going to have to kind of do that. In B, we're going to increase the angle of the incline slowly. And of course, at some point, it is going to slip. And I've just got to draw a free body diagram. I don't know what the angle of the incline is anymore in B, but that's going to be my unknown. So let's try to draw a separate free body diagram. We've got the same weight force, 2 times 9.8, going down. This angle right here is no longer 20 degrees. I'm just going to call it Greek theta for that angle and try to figure out what it is. There's still a normal force. We'll call it Fn. And there's a static friction force, of course. The more I tilt it up, the higher static friction's got to push up to keep it from sliding down the plane. And we're interested in what's the value of the angle so it's just about to slip. That would mean when this is the maximum static friction force. So in this case, it is appropriate to use the formula mu s times the normal force. So same three forces, but now we're imagining someone's tilted it so it's just about to slip. Friction's still pushing up the plane, but it can't hold on anymore. If you tilt it up, friction won't be able to support it anymore. So I'm going to choose the same axes and see what happens. You know, you could go for it and say, well, let's just try the x one. Well, okay. If I try sum of the force x components, is equal to MAX. It's going to involve theta. Maybe I could just solve for it. Well, that would be, let's see, the mu static times the normal force. Let's see. What was mu static here? 0.45. 0.45 times the normal force. Oh, yeah, I'm going to have to solve for that normal force. And then this weight force also has a non-zero x component. It's negative, and it corresponds to the length of this side, minus mg times the sine of theta. And it's that theta I'm trying to get at. And again, I'm imagining a situation where it's about to break free, but it's just sitting there. So again, AX is 0. So the right-hand side is 0. So I see I'd be in pretty good shape if I could only figure out what the normal force is. And I'm going to figure that out from the y components. Right? So let's go over here and do the sum of the force y components equals MAY. That's also 0 because it's not moving, not accelerating in any direction, so AY is also 0. Certainly, the normal force comes in with a plus sign, but this weight force also has a negative y component. And going from tail to tip, we're going along the negative y direction. Minus 2 times 9.8 times the cosine of theta. And that's equal to 0, and therefore the normal force is 2 times 9.8 times the cosine of theta. So let's just substitute that in here. 2, 9.8 cosine of theta minus 2 times 9.8 times the sine of theta, and that's equal to 0. Oh, yuck. How do I solve for theta? I've got an equation that, I've done 9/10 of the work here. I've got an equation that only involves theta, but how do I solve that for theta if I've got a theta in a cosine here and a theta in a sine over there? Anybody have any idea? I wouldn't put a problem like this on the exam because most people, just don't have enough intuition. But you know enough to figure out how to do it, probably. If we put them on opposite sides and then divide the sine by the cosine, we get a tangent. And then you can take the inverse tangent to solve for theta. So, the important work we've done in getting to here. But if you really wanted to solve this, let's see. This is negative over here. I could put it over on this side with a plus sign. So maybe that would turn it into this kind of equation. And then I'm going to divide both sides by cosine of theta. Well, I guess the first thing I can do is there's a 2 on both sides. There's a 9.8 on both sides. I can cancel those. And if I divide both sides by cosine of theta, this cancels out, right? Cosine theta over cosine theta. And this is tangent of theta. So I get an equation that says tangent of theta is 0.45, and therefore theta is the inverse tangent of 0.45. Apparently that's 24.23 degrees. So it was only a little bit more than the 20 degrees. So it was sort of close to slipping, but it had to go an additional 4 degrees before it would really be at the breaking point. This isn't really important that you know how to do that kind of trickery to solve that equation, but it's just an example of how to think about friction there. Any more questions on that one? Why don't you go ahead and try problem 10 if you haven't gotten to that yet. This one is not on an inclined plane, but it involves friction and acceleration while just moving horizontally. All right, let's come together and solve it. Looks like most of you are finishing up the second part now. The third part we'll find out that you already knew the answer to just by virtue of doing what was above. So we've got a book that's sitting on a horizontal seat of car, kind of an idealized situation, and the car is accelerating forward at 1.8 meters per second squared on a flat, straight road. So it's just accelerating on a flat road going straight ahead. The 2 kilogram book is initially being held in place so it doesn't slide while the car is going faster and faster. You may have some intuition, right, that as the car is going forward, if you're sitting in the car, it seems like everything wants to slide back, right? I mean, that is a non-inertial reference frame in that case, so things are a little bit weird, but from your point of view, things want to kind of slide back. And just to make sure that it doesn't slide back, I'm holding it with my hand. But at some point, while doing this acceleration, I let my hand go. That's the idea. And the question is, will it start sliding against the seat? I was holding it so it was in a static situation, right? Not moving relative to the seat. And once I release my hand, I take away one of the forces. Are the conditions such that we've exceeded the maximum static friction force that can be applied, and it starts sliding relative to the seat? So my goal is to, A, figure out what the maximum static friction force is, and then B, see what static friction force is required at this acceleration, and see if that required friction force to keep it going in this acceleration exceeds the maximum static friction force. If the required force that would have to be keeping it at that accelerated at that rate is bigger than the maximum static friction force, it's going to start to slide, because friction is the only thing keeping it in place. So let's draw just a crude diagram. Here's the seat. Here's the book sitting on top of it. And let's assume the car is at every instant moving in that direction with the acceleration that's given, 1.8 meters per second squared. And let's draw a free body diagram. You know, really the only sensible thing here to draw a free body diagram for is the book, or at least given its mass. It's a 2 kilogram book. And let's draw the forces that are acting on it. Help call out some forces. What one should I put in there? Normal force, in this case, weight force, friction. Which way is the friction force acting in this case, to the right or to the left? It's acting to the right, right? Because if it's accelerating in that direction, we all know things that are, when you're accelerating forward, things that aren't pinned down tend to kind of roll back on the seat. So it wants to go back. That means the friction force has got to be holding it in that position. So in this case, there's a friction force. We'll call it the static friction force in that direction. And maybe just to remind myself what it means, if that's the only force and it's accelerating with this acceleration, I'm going to put REQ for the required static friction force. Okay, and let's put some axes on there. In this case, nothing's tilted, so let's, as always, take one of the axes along the direction of the known acceleration, you know. So there's a free body diagram, axes. And so I've got to figure out the required static friction force, and then in a separate calculation, figure out what the maximum static friction force is, and then we'll think about those. So first this. The sum of the force x components equals MAX. Sum of the force x component, well, this has 0x component. This has 0x component. That's kind of nice. So it's just whatever the static friction required force magnitude is equal to the mass of the book times the acceleration. And was it 1.3 or 1.8? 1.8. It's in meters per second squared, yeah? Yes. Yeah. Did I write something down wrong? No, kilogram is the SI unit for mass, and meters per second squared is the SI unit for acceleration. So I'm putting in all SI units, and that's the nice safe place where I don't have to really think too hard. I can just calculate all the numbers, and when I solve for something, I know I'm going to get SI units out because we're using dimensionally balanced equations. So remember, not grams, but kilograms is the SI unit. So 2 times 1.8, okay. In this case, that's 3.6. And that's a force, so it's in SI units of Newton since I put everything in SI units. So that's the required force that would be required to keep it accelerating at that rate. Now, there's no guarantee that static friction can hold on that tight, so I separately now have to calculate what is the maximum magnitude force that the static friction can push with. And then we're going to compare it to this number. That is the mu static times the normal force. Is everybody okay that in this case, because there are only 3 forces, one of them is horizontal, so these 2 vertical forces have to balance each other out because it's not accelerating along the y direction. Okay, if it were accelerating, then they wouldn't balance out. They couldn't balance out. But in this case, the y coordinate's staying constant as it accelerates along this direction, so of course it's not accelerating along y, and that means these 2 forces, y components, have to add to 0, and that means Fn is 2 times 9.8. Okay, so our mu static in this problem is 0.35, and Fn is 2 times 9.8. Okay, so if you throw that in your calculator, 6.86 according to my work I have here, newtons. So friction can push with 6.86 newtons before it gives out and things start sliding. We're only requiring 3.6 newtons of force to keep it accelerating at this rate. So when I release my hand, and then the free body diagram looks like that, right? Before, maybe I had some hand force going forward, but in this case, it looks like it will hold on. It won't slip is the way I phrased it there. Question on A. Okay, B, what is the maximum acceleration the car could have so the book barely does not slip? Well, in this case, we know that maximum acceleration is bigger than 1.8 meters per second squared, because at 1.8 meters per second squared, it wasn't even close to just barely hanging on. So in part B, you know, normally I might draw a free body diagram, but out of laziness here, I'm just going to say, oh, the only difference in part B is that this isn't the puny required static friction force. We're going to make it so it's barely hanging on and say it's going at some bigger acceleration. Let's solve for that acceleration, x component. Okay? So in B, same calculation. In fact, you know, maybe I can just alter my stuff down here. Same stuff. Well, let's just do it again. Sum of the force AX, sum of force x components equals MAX. The maximum static friction force, so we already calculated what that was. That's 6.86 newtons. And it comes in with a plus sign, right? It's still pointing along the plus x direction. This has 0x component. This has 0x component. So that's all that goes on the left-hand side for that summation. That's equal to the mass of the thing in the free body diagram times whatever that maximum, I might, you know, call this, if we're putting in the maximum static friction force, then this is going to be the maximum acceleration we could go accelerate with and have it just barely not slip. So when I divide that 3.43 meters per second squared, that's B. And then C, if the car accelerates at 1.8, what's the friction force magnitude on the book? I'm not sure why I asked that down there, but in any case, we already found it out up here. Friction force magnitude was 3.6 newtons. Okay, more questions on that? Those are 2 kind of generic problems having to do with friction. Maybe the inclined one, I would say, is more complicated, although this one can be sort of conceptually confusing because you have to really separately calculate the maximum and the required and compare them. All right, So that's static friction. There were more examples in the practice problems that I gave you. So now I'm going to open it up maybe for 15 minutes or 20 minutes, and then I'll pass out that old exam, and you guys can just independently work on it, ask questions as you like. And if there are common questions I'm noticing, I can do something at the board that way. And I'll provide you, just like I provided solutions to the stuff I sent over the weekend, I'll give you scanned solutions through email to this stuff. So, questions on homework that's due tomorrow. It's due at midnight, but don't wait till midnight to finish it. That's a bad idea on the night before the exam. So really now is the time to get those questions answered, or your last ones in the middle of the day tomorrow as well. Homework or the stuff, anything exam related, like the practice problems I gave you for the exam, I'm happy to answer anything. Yes, Jeremy. Chapter 3 homework? Okay. I've got my printed copy, so if you describe it to me, I might be able to find. Two walls. Yeah, something accelerating along the y direction. I remember that one. And do you have a specific question on it? Yes. At what angle with the wall will the particle strike? I spoke with several people about this problem after class a couple of times, so seems to be a popular problem. First thing we have to figure out is, well, what do they mean by that angle? And, well, you kind of have to know what the angle with the wall is. It means the same, when I say the angle with the horizontal, you know, if a particle is coming up and I say, what angle does it make with the horizontal? It means on the track that it's going on, how far to the direction that defines the horizontal. So it's going to be the same thing here, but with respect to the wall. So here, I'll give the numbers in my version of the problem. It moves towards the opposing wall at 5.7 meters per, so right here at this wall, it's already moving at 5.7 meters per second, but it also is accelerating upward at 2.3 meters per second squared. So if it weren't accelerating, of course, it would just go straight across, but it starts going more and more and more in the upward direction. So its path, which you probably figured out because you did part A, starts to curve more and more upward as time goes on. It's got a constant acceleration there. And so the approach in part 2 to find the angle with the wall, what that means is right at this instant, right when it's about to strike the wall, it's got a certain velocity vector. And the angle with the wall means that angle. And so my goal is, well, if I could find, you know, maybe if I call this x and this y, if I find out what Vx final and Vy final are, well, I didn't draw in the best right triangle there because it doesn't include my angle. Let's do it this way. This is Vx final, and this side over here is Vy final right there. So there's a little right triangle that includes my angle. So if I know those two sides, I could say tangent of theta by SOHCAHTOA is Vx over Vy. So part of the question is, well, do you know what those words mean, the angle with the wall? And that's a legitimate confusion. Several people asked about what that means. Okay, so we need to find, I don't know if that answers your question, or do you want to find? Okay, so we want to find, we've got a time period here. This is initial, right, when it's leaving this wall, and final one is when it's about to smack into that wall over there. We're given the separation between the walls, 18, these are my numbers, 18.4 meters. Okay, so we're going to call this initial and this final, and we're interested in finding Vx final and Vy final. Do we know anything about those to begin with? What Vx final or Vy final is without doing any work? Yeah, Vx is not going to change because Ax is 0. When something's not accelerating, it keeps that same, if it's not accelerating along a certain axis direction, it keeps that component of the velocity. So, you know, we might say, well, look, Vx final is Vx initial plus Ax times t, but Ax is 0. It's not accelerating along the x direction, only along the y direction. So the final Vx is the initial Vx, and in this case, that was 5.7 in SI units. Okay, meters per second. So our first job is to find Vy final. It is accelerating in that direction. Well, let's write down some equations. We've got a couple that tell us what Vy final is. One of them is Vy final is equal to Vy initial plus Ay times t. I certainly know what Ay is. It's 2.3 in SI units, but I don't know what t is. Is there any way I can figure out what t is? Because I really haven't used the 18.4 yet either. Yeah. I can't remember what the second one is, but I would use the x versus t equation, whatever one you think that is. X equals x0 plus vx0 t plus 1/2 ax t squared. So if I take my origin to be right here, I didn't do a very nice job of doing that, but let's take x equals 0 to be at the left wall. Then x final would be 18.4, x initial is 0. Vx initial is 5.7 times t, and Ax is 0, right? It's not accelerating along the x direction. So that tells me t is 18.4 over 5.7, whatever that number is. That number of seconds. And then I can substitute down here to find Vy final is, well, it started off with 0 y velocity component. Ay is 2.3, and whatever that number is. So now I know Vx final and Vy final. I know the sides of this right triangle, and I'm going to use tangent of theta is opposite over adjacent. So in this case, it's not y component over x component, but rather for the definition of angle theta we have there, right? It's not the angle with the horizontal, so we shouldn't just go automatically into that mode. But from the right triangle, it's the opposite. That's Vx final over adjacent. That's Vy final. And then take the inverse tangent. Good. Any other questions on that one before we move on? Noah? Okay. Yeah, I'm looking for, I do have a copy of these, but that's not it. That's chapter 2, or sorry, chapter 3. Here we go. So there is a car with two forces. We're looking down on top of a car. Again, I'm just going to do my numbers in here. 30 kilograms is what's labeled on my car, and we're looking down from the sky in this picture. And here's the direction straight ahead. There are two forces being applied to the car. 402 newtons, which is being applied at an 8-degree angle to the horizontal in the direction above the horizontal. It's not really horizontal because we're looking down at the car like this, but relative to that dashed line, it's above it in this projection. And then there's another force which is 327 newtons, and it's at an angle of 25 degrees on the other side of that dashed line, which is straight ahead. And the question is, what's the magnitude of the resultant of these two forces? The resultant just means the sum. So all we need to do is add the two forces and then figure out its magnitude. So how might I do that? Was your question on A, or is it the next part? Yeah. Yeah. My memory is that a lot of people ask about this question on this homework problem. So when we add them, of course, I could do the parallelogram method, and I'm not drawing the best parallelogram. It's not necessarily going to add to something along the dashed line there, right? In this case, but if I create a parallelogram out of these ones, then the resultant would kind of look like that. It would go from the common tails to the opposite side of the parallelogram. So this is what I might call F resultant, to use the terminology in the problem. And I want to find the length of that vector. So how could I do that? Haley. Add them individually. That gives me the x and y components of the resultant. And then I finish up with the Pythagorean theorem, right? So I would say, if I say, for example, x is along the dashed line direction and y plus y is along the upward direction in my diagram, then I would, let's just call this F1. I don't know if they're labeled like that in the diagram. We'll call the upper one F1. So I want to calculate F1x and F1y and F2x and F2y. And then that will allow me to calculate F resultant x and F resultant y. Okay, so F1x, well, that's just this distance in that right triangle, which is 402 cosine 8 degrees. F1y is 402 sine 8 degrees. F2x is, well, it's positive because I'm still going in the positive x direction as I go from tail to tip. So that would be 327 times the cosine of 25 degrees. F2y is negative, right? Because it's actually going down, and I chose plus y to be up. Minus 327 times the sine of 25 degrees. And so for the resultant, I would have to add those two, right? So that would be 720, no, I just need to calculate it, my calculator, because I've got different cosines and sines in there. But the idea is this F resultant is going to be the sum of these two x components, the resultant x component, and the resultant y component is going to be the sum of these two y components. And then what that's telling me is it's hard to draw it in this diagram because it's such a small angle the way I've pictured it here. And I think it is a small angle. But what I've found, the y, I'm expecting, at least from my diagram, it looks like it's a negative y component and a positive x component. I don't know if I've drawn that realistically, but essentially I know the length of this side of a right triangle and this side of a right triangle, and I want to find this hypotenuse there. And I can use the Pythagorean theorem. The square root of this squared plus this squared would give me the resultant. And then in part 2, they're asking for the angle in the usual sense of positive angles going up and around like that. So it looks like I could just take the arctangent of the y component over the x component, and it would give me that angle where negative angles mean down here and positive angles are up there. Noah, did that help on that one? Okay. More questions on this particular problem? Yes. Right. Does that make sense in terms of the picture, right? You got to, I mean, I didn't picture adding the x components and the y components, but when we add vectors, if we want the components of the sum vector, we just add the individual components, x components and separately y components. What else can I help with? Well, so if I've calculated these two things, right, the usual picture, let me just imagine that my resultant looks like this. Well, the angle they're talking about is relative to the horizontal, where positive angles are up and negative angles are down, so it looks like that, right? So we have found F resultant y component and F resultant x component, and so we're going to use the usual tangent of that theta is opposite over adjacent, and then take the inverse tangent to calculate the angle. If it's like I've drawn it here where the resultant is going down a little bit, I'm expecting a negative angle out of there. I have no idea if I drew that correctly. They show the two vectors on there, but kind of hard to tell. I think in my version it looks like it might be a negative angle, but we'll find out when we do it. Yeah, and that's generally true, that when we have x and y components of the angle of a vector, regardless of how we got it. In this case, we had to add something. But if you have a vector and you've got its x and y components, and you want to find that angle in the standard position where these are positive angles and these are negative angles, and that's the x direction, tangent of theta is the y component over the x component, and then you can take the inverse tangent. And the only thing you have to remember is that, you know, if your vector isn't pointing over into quadrants 1 or 4, you might have to add 180 degrees after you take the inverse tangent. But in this case, it is clearly going to, I think for all the versions that are on here, it's all going to be pointing somewhere to the right and up or down. So you'll either get a positive or a negative angle between minus 90 and 90. What else can I help with? You know, looking through this homework assignment, there are a couple that are somewhat tricky, but I would say relative to the chapter 3 homework, it looks more straightforward. You've got to use all the techniques that we have, but there are only a couple that are sort of oddballs, like if you're looking at the homework problem 20 in here where there's a train car that's accelerating and they're telling you the angle that a light is on the ceiling is going backwards, right? Because just like your groceries like to slide back on the seat if you have them next to you as you're accelerating that direction. Similarly, if you have a light that normally hangs straight down, if the train is accelerating in that direction, the light's going to be at some angle like that. And by measuring that angle, you can figure out the acceleration. That one's a little bit of an oddball problem. Sure. Let's do that one. Don't be shy about asking for other homework stuff. That's what we're here for. And that's why I kind of gave us a little bit more time today rather than moving forward, rather to just idle and think about the stuff that we've been learning, because we're in the middle of this homework now, and we just only learned about this stuff kind of late last week. So we've got a train accelerating to the right. So we'll draw a picture, a cross-section of the boxcar. Here it is. It's accelerating in that direction. And the claim is that if it accelerates at a constant rate, you'll find that a light fixture on the ceiling attached with some cord. In my version of the problem, they tell us the light fixture has a mass of 7.7 kilograms. We'll find out that it doesn't really matter what the mass is. Someone measures it, and they find out, in my version of the problem, that this angle is 44 degrees relative to straight down. And we're supposed to, from that, find the magnitude of the acceleration of the car. And the idea is, well, if the car is however fast it's accelerating, if this thing's sitting just stationary relative to the car, that's the acceleration of the light fixture too. So let's do a free body diagram for the light fixture. I'm going to draw it, sort of tilted like that. There's my 7.7 kilogram light fixture. Of what forces are acting on it? Well, certainly the weight always acts on it. 7.7 times 9.8. That's the Earth pulling down on it. The only other thing that I can see that's reaching in and pulling on it is the tension from the cable or the cord or whatever you call it that's attached to the light. And it is along that direction that's pictured there. So I'll call that tension T. And I think those are the only two forces in the free body diagram. And our goal is to find that unknown acceleration. Okay, step 1, free body diagram. Step 2, attach axes. Do you think I should attach horizontal and vertical or tilted to line up with the cord axes here? It certainly is tempting to do tilted, but that's the wrong answer here. Do you remember what my rule of thumb is for how to choose the direction of the axes? If you know the direction that something is accelerating, always choose one of your axis directions along that known acceleration direction, because then there's only one unknown acceleration component. Otherwise, if I tilt them and I know it's accelerating in that direction, I'm going to have an unknown AX and AY. I'm just making more work for myself. So following that, and most people I've found usually choose tilted, the wrong choice first, or the more complicated choice. Okay, in that case, I'm going to need an angle here. Let's see. We know that this angle here is 44 degrees, and that's fine. That's a good angle. This is 44 degrees there. Sorry, I'm writing sort of small for those of you in the back, but that angle at the top of that right triangle is 44 degrees. The t is the length of that vector, because we'll need x and y components. Now it's ax that I'm after, so I'm just going to do sum of the force x components equals max and see if we're good. So let's start out there. Sum of the force x components equals max, and it's that ax I'm after because ay is 0. So ax is going to be how big the acceleration is. This has 0 x components, so that's good. This one has a non-zero x component. I want to find the length of this side in the right triangle. The magnitude, the magnitude of this force is just T, the unknown tension. To get from the hypotenuse, which is of length T, to the x component side, I have to go across the angle. So that means I have to multiply T times the sine of 44 degrees. And it comes in with a plus sign because T is pointing more or less along the plus x direction. And that's it for that side. And that's equal to 7.7 times the unknown ax. But I'm kind of out of luck, at least for an easy solution, because I have the thing I want, but another unknown in there. I don't know what T is. So let's hang on to that and do the only other reasonable thing, which is the sum of the force y components equals may. Let's see. To get from the hypotenuse here to the y side, I have to swing through the angle, so that's a cosine. I start with the t and multiply by the cosine of 44 degrees. That comes in with a plus sign, because it's more or less along the plus y direction. Minus 7.7 times 9.8. And those two have to also balance out, right? Right? No. Yes, they have to balance out in this case because ay is 0. It's worth thinking about. You've always got to, don't make an assumption that it's automatically 0, but in this case, there's no acceleration along that direction. All the acceleration is along this direction. That's why we chose our axis that way, so we could take advantage of that. So I can now solve for t here. And, you know, it is what it is. Put it in your calculator, put it up there, and solve for ax. That's the approach. You're welcome. Anything else before we? Yes. So I know it's kind of hard. I'm just going to blow up this little right triangle here, right? This is the cable direction, and there's the unknown tension T in it. And let's suppose we're going to try to find the x component, this side right there, right? If this angle is 44 degrees, that means this angle right here is 44 degrees, right? How do I get from the hypotenuse to that side? I go across the angle. And whenever I go across the angle, I multiply by the sine of the angle. I'm not sure I understood that, but it is true that if this angle were 44 degrees, then the x component would be t times the cosine of 44 degrees. But in this case, that's not the angle we know. And so when you switch to the other angle, cosines turn into sines. So always good to sort of think about it with fresh eyes. Don't just assume x is always cosine and y is always sine. It depends on what angle you're given. I could have figured out this angle and then switched the cosines and the sines, but that was problem 20 in the homework. You know, but if you look through the homework, there's a lot of things where there are three objects pushed up against each other, or things connected by cables, and some pulley problems too. So there's quite a variety of stuff in there. So this again is some, you're welcome, old exam. And you're certainly welcome to be silent and just work on it, but there's no reason everybody has to do that. So if you got questions, now's a good time to ask. If you're not sure how to approach something, don't sit and spin your wheels, because I'm here to come over and look and see what might be a good way to go forward. Yeah, this one is 1, 2, 3, 4, 5 pages, and I think our exam, I haven't pressed print yet, but it is 5 pages, and that's usually my go-to length. You know, all kind of hinges on if there's how long a page takes. But this particular one starts out with some conceptual problems. Some exams I emphasize more conceptual stuff and sometimes less. But you know, you can look through here and sort of say, oh, look, an elevator problem. That's no surprise, hopefully, because we've done a bunch of those. A graphing position, velocity, acceleration versus time problem. Hopefully that's not a surprise, because I told you that was probably going to be on the exam. Something with inclined planes. That's not a surprise. The last problem kind of looks like a kinematics problem, right? Something is falling off, you're rolling something off a ledge and it's falling into a hole. And then there's something with friction here, where something's sliding along, where there's a region where it's frictionless and then there's friction acting. So I would say you should have in your head what kinds of problems you expect on there. You know, there may be one oddball one, but most of what you're seeing on the exam should be the bread and butter kind of problems, not some of the oddball ones we've seen in the homework where it's like, oh, that's kind of nothing like we've seen. That shouldn't be most of the exam. Yes.
Would I just change my axes to be like that instead of slanted then?
Not necessarily. If you know the direction of the acceleration, you always want one of your axes to be along the direction of the acceleration, which means if I'm choosing my axes to be tilted, I'm going to have to, multiply by the cosine or sine of an angle to get x and y components of that 100 newtons. I can't remember if that's accelerating in that part or not. Is that one moving at constant speed? Part of it was moving at constant speed. And
It's asking for the acceleration.
yeah, so in this case, I know, when you're pushing like that, it's not going to launch off the plane. So it's going to be accelerating along the direction of the plane. So choose your axes parallel and perpendicular to the plane. And then that 100 Newton force in there is going to have to, you're going to have to figure out what its x and y components are in that tilted coordinate system. Maybe I'll put some of the answers up here just so you have something to check against. possible for an object to experience a constant non-zero acceleration between times t by t2? Or does it have zero displacement for this time interval? So that would be like, I throw a ball in the air. What? If air resistance is negligible, it's going to have a constant acceleration, right? Is there any way I could choose 2 times so that it would have zero displacement between those times? Yeah, then it wouldn't have gone any distance between those 2 times.
I thought that means like between times 2 and 2 would be like the entire time between.
Yeah, I mean, that seems like there's, yeah. I mean, it's not the entire, that was not the intent of that. It seems like, I'm not sure what I could be thinking of if I were saying the entire time, then it would just have to sit still. But, you know, if you're ever confused or not sure what to think of, definitely ask questions about that on the exam. Don't be shy about getting clarification if something.
And then for this one, I thought it was no, it's yes.
Is it possible for an object to have a non-zero acceleration vector in a period of time during which its speed remains constant? Yeah, the key is speed, but not velocity. So something can be moving along at constant speed, it's accelerating. Anytime something's velocity vector is changing, it's accelerating, but its speed is constant. So have the object move along some curvy path at a constant speed, and we're guaranteed that it's going to be accelerating. Remember that what we got acceleration from was the change in like Vx over delta t. If Vx is changing at all, right, and if something is going in this direction and starts to go up, keeping its velocity constant, its Vx is going to get smaller. Vy is going to get bigger if I'm keeping the speed constant. So if your velocity is changing in any way, you have a non-zero acceleration. But you can do that and have your speed remain constant.
Question 1 is 12 points, so would that be like 1 point for the answer? And then
I mean, honestly, I can't remember how I graded it, but it may have been, you know, 2 points and 2 points or something like that. You know, because sometimes someone give the correct answer, but then a not clear or incorrect explanation. But I can't remember exactly how I graded it, but it was split between it. Mm-hmm. For 2? Just look at my version to see here. So the tension is 15 newtons. So why are you not using the mg in, we're doing the sum of all force y components, right? Certainly the tension is one of them, but the Earth's gravitational force, mg, is another one, right? If you're choosing plus y down, then the if this early is your plus y, then that 15 should come in with a minus sign, right? Because its y component would be negative. And then the m times 9.8 would be positive, right? I can't remember, it's accelerating downward. Yeah, that's fine to do it that way. There's nothing wrong with that, and you're not making any more work for yourself. So let's see. In this case, here's how I would draw it. I've got an unknown m, there's a t going up, and m times little g going down, right? Let's do it your way. And sum of the force y components equals may. Let's fill that in. mg comes in with a plus sign. Are you with me, Anna? Right? Because it's going along the plus y direction, whereas the t comes in with a minus sign. The mass of the thing in the free body diagram I'm calling capital M. And the ay is 3. And I guess we know what t is. It's 15, right? So I need to, and you know, I can put in a 9.8 for this. So I got to combine together those two m's in this case. I didn't draw the graphs up here because I didn't want to give it away, but if you have questions, I'll bring mine over and we can compare.